Ion exchange chromatography is also a very important analytical technique exclusively used for the separation of ionic compounds. This is also belonging to liquid chromatographic technique. Here, the stationary phase will be a solid and the mobile phase will be liquid. So what is the principle of ion exchange chromatography? What kind of stationary phases are used? What kind of mobile phases are used? What is the mechanism of compound separation takes place while using ion exchange chromatography? And what are the properties of the stationary phases while performing the separation by ion exchange chromatography? And what should be the fundamental requirement in order to choose the stationary phase to perform ion exchange separation? All these things are very, very important. Let us go one by one. So in today's discussion, this is going to be the outline of my presentation. So we shall discuss on principle of ion exchange chromatography, the ion exchange resins which are commonly used as stationary phases. What are the properties of ion exchange resins, preparation of ion exchange resins, what is the equilibrium aspect involved in the separation of compounds by ion exchange chromatography, selectivity of the resin and ion exchange capacity of the resin, and moreover the applications, some important applications of this ion exchange chromatographic technique we shall discuss. And apart from this, we have to touch on ion chromatography, in which single and double column ion chromatographic techniques have also needed to be discussed, because we will adapt the principle of HPLC in order to perform the ionic compounds by ion exchange chromatography. While we use the detectors, while using the detector, we may use one column or double column. And what is the purpose of usage of the double column? And what are the principles and advantages of single column ion chromatography? We shall discuss one by one. So let us look on definitions of some terms such as chromatography. Chromatography, you know the definition of chromatography. Chromatography is nothing but it is an analytical technique which is used for the separation, isolation, and quantification of the chemical components which are present in the samples, irrespective of the origins, whether the compounds may be simple or macromolecule, whatever it is. We can separate the compounds by using a technique known as chromatography. Here, in any chromatographic technique, there must be two phases. One will be the stationary phase and another one will be the mobile phase. And the relative elution of the solute molecules are dependent on several mechanisms. And all those mechanisms we have discussed. So likewise, what is the mechanism involved in ion exchange chromatography is also very important. And we shall understand about resins, what kind of the definition can be given for resins, and what is the meaning of ion exchange process, what is the meaning of cation exchange and cation exchange resin, what is the meaning of anion exchange and anion exchange resin, and the meaning of ion exchange chromatography. So after understanding the definitions of all these things, then only we will become more comfortable in order to derive the procedures to perform the separation by ion exchange chromatographic technique. You know, chromatography, meaning of chromatography, I need not to explain that again. So let us look at the definition of resin. Let us see a common term, resin. There are many or plenty of resins which are available naturally, or even man-made resins are also available. If you go to market, you can find out many resins. And the resins are polymeric substances which are solid in nature. Moreover, apart from solid nature, they may be highly viscous. They may be highly viscous. They are derived from the plant origin, or they can be synthesized. Human can synthesize, a chemist can synthesize a resin with respect to its requirement. We can fix the requirement of the resin, what kind of resin we have to prepare, and according to the requirement, we can prepare the resin. So, resin is a solid or a highly viscous liquid, highly viscous substance, sorry, which can be derived from either plant or which can be synthesized manually. You can see here a very important natural substance, a gum, natural gum. You can see this by the acacia tree. So acacia tree is well known for producing the gum. In our age-old days, we used to use this gum in order to stick the papers or in order to stick something else in our school days. I don't know whether you people are using this or not. So this is a resin. This is a resin. This is not a pure solid. This is a highly viscous liquid. This is a highly viscous liquid. And this has very good flow ability. And of course, chemically, we can say that this is also having a certain degree of cross-linking. So that's what it is having sticking ability. Because of the property of this resin, which we can get naturally, the sticking ability of this resin is obtained due to the property of this particular resin. And this is a man-made resin. And this resin is available in the market with variety of brands. Say, for example, Dovex1. If you take Dovex1, that is chloride form of resin. If you take Dovex50, that is hydrogen form of resin. Amberlite, zeolite, duty, all these are brand names of the resins. So the resins will be looking like granular species, which will be having very good flow ability, and they will be having very high viscosity. Because of their very high viscosity, their rapid flow is very less. They don't move rapidly, and the density of the resins will be always greater than water. That's what they have the capability to create a bed whenever you force that to be present in a column or a surface of a flattened object. And this is a man-made resin. As I told you, there are a variety of brands of man-made resins are available, and these are also called as synthetic resins. And clay minerals, even clay minerals which are available in your villages, hill areas, or in your lands, these clay minerals are particularly made by silica, and these silica particles may be modified naturally, or even we can modify these clay minerals which are naturally available silica, and we can modify them to any extent in order to get the required resin. And some synthetic organic resins are also available in the market. Most commonly, these synthetic organic resins are widely used resins in order to perform ion exchange chromatographic separation. And similarly, some inorganic materials can also be used as resins, mainly zirconyl phosphate, ammonium 12 molybdo-orthophosphate. Because of the property of these molecules to have bulky fixed cationic or anionic groups with the availability of free ions which are able to move, Therefore, these compounds can be used as resins. So now you understand the definition of resin. Resin is a solid or which is a highly viscous substance that can be obtained from plants, or even we can synthesize the resins. They have very good flow ability, and they possess certain chemical characteristics. Because of these chemical characteristics, we will use them for the separation of chemical compounds by ion exchange chromatography. Then let us move on to the definition of ion exchange. So as the name is implying that the exchange of ions of the same charge between an insoluble solid and a solution in contact with the solid. So you have a solid, that solid will be having a free ion. That free ion will be moving in nature. So the ion which is moving can be replaced by the ion of the likely charge which is present in the solution. This is called as ion exchange process. So ion exchange process is nothing but the exchange of ions of the same charge between an insoluble solid and a solution which is contact with the solid. You can look at this diagram. So here I have presented two types of resins. This is the one resin and this is the other resin. Here this resin part is called as polymeric surface, and H plus ions are freely available over the surface of this resin. Similarly here, this is the polymeric surface of the resin, and OH minus ions will be freely moving. Hydrogen ion or OH minus ions are called as free ions. Here the charge on the hydrogen is positive, and here the charge on hydroxide is negative. So this resin is in the form of hydroxyl form, and this resin is in hydrogen ion form. So this resin is called as hydrogen form of resin, and this is called as hydroxide form of resin. Or also, this is called as cation exchange resin, and this is called as anion exchange resin. Because here the hydrogen ion is a cation, here hydroxide ion is a anion. Cation is having the ability to get replaced by other cations, and this anion is having the ability to get replaced by other anions. Therefore, this is called as cation exchange resin, and this is called as anion exchange resin. I have denoted here the resin will be having fixed anionic group and movable cationic groups. So this is a cation exchange resin. Cation exchange resin is a resin in which the resin will be having a fixed anionic group which is attached to the polymeric surface of the resin and freely movable cations which are able to be getting replaced by other cations. Similarly, the anion exchange resin is a resin in which a positively charged species is attached to the polymeric surface of the resin and the negatively charged species will be in motion. So here H plus ion is in motion, here OH minus ion is in motion. H plus ion can be replaced by any positively charged species. You can see here sodium ion, and OH minus ion can be replaced by chloride ion. This process is called as ion exchange process. So when you take a medium, containing cation exchange resin in the hydrogen form, and through that medium, if you pass a solution of sodium chloride undergo rapid ionization to get converted to sodium ion and chloride ion. As a result of traveling of sodium chloride or the ions like sodium ion, chloride ion through the medium containing cation exchange resin, this cation exchange resin is having more affinity to get exchanged by sodium ion in place of hydrogen ion. So while sodium ion and chloride ion are moving through a glass column, assume it is containing a cation exchange resin and the resin is in hydrogen ion form where sodium ions are going to be replaced in order to convert the resin into this particular form. So all those hydrogen ions have been replaced by sodium ion in order to convert the resin which was present in the hydrogen ion form has been converted to sodium ion form now. And whatever the hydrogen ions which have been replaced by sodium ion, they are going out of the chromatographic column during the elution step. So these hydrogen ions will be coming out from the chromatographic column. The number of hydrogen ions or the quantity of hydrogen ion released from the chromatographic column is with respect to the amount of sodium ion or amount of cations which have been replaced in place of hydrogen ion. So this process is called as ion exchange process. Hydrogen ion has been exchanged by sodium ion to convert the resin into sodium form. Consequently, the hydrogen ion is going to be eluted. This process is called as ion exchange process. Similarly, you can look at the other resin. Here, the resin is in positively charged species attached to the polymeric surface. This is not moving in nature. And OH minus is the negatively charged species. This will be moving in nature. This will be moving and this will not be moving. Here, trimethyl ammonium ion. This is a quaternary ammonium ion which is tightly binded to the polymeric surface. That's what it is not able to move. But this is freely available over the exterior of the resin, anion exchange resin. Therefore, whatever the anion which are having more affinity towards this trimethyl ammonium ion, they will be exchanged when you pass the solutions containing anions such as chloride through the anion exchange resin containing hydroxide ion. So you take a anion exchange resin in the form of hydroxide, where hydroxide is going to be the free ion or mobile ion. If you pass a solution of sodium chloride through a glass column or a chromatographic column containing anion exchange resin, the anion in sodium chloride is going to be chloride, and chloride is going to exchange hydroxide ion in order to convert the resin which was in OH minus form to chloride form. So whatever the hydroxide ions exchanged by chloride ion, they are released out, they will be coming out of the chromatographic column. Here, The amount of hydroxide ion released is equivalent to amount of cations exchanged. The amount of hydroxide ion released is equivalent to amount of cations exchanged. So this process is called as ion exchange process. So the exchange of ions of the same charge between an insoluble solid and a solution in contact with the solid is called as ion exchange process. So you don't get confused. H plus ion is a cation and it is going to be exchanged by positively charged species. Similarly, OH minus is anion and it is going to be exchanged by the anion such as chloride. You can see here the resins, the general structures of resins. Of course, I will explain how do you synthesize the resin, what is the chemical reaction going to be taken place during the preparation of the resin. We shall understand about that later. Assume this is a strong cation exchange resin. Here, this is going to be the polymeric surface. You can look at the benzene structure. All those benzenes have got SO3H group at para position. Each and every benzene ring in its para position having SO3H group. So when you make this resin to contact with any aqueous solvent, this sulfonic acid undergo dissociation or hydrolysis or ionization to get converted to SO3 minus and H plus. So this is going to be the resin. This is going to be the resin. SO3 minus is the anionic group which is attached to the polymeric surface, and H plus ion is going to be the positively charged species which will be moving in nature. So you use this as a resin, and whatever the cationic solutions you are going to pass through the chromatographic column, those cations are going to be exchanged in place of hydrogen ion and they are released out. The hydrogen ions are going to be released out. This is a very simple example to express the structure or the action of cation exchange resin. You can see here, this is a amberjet 1200H or amberlight IR 120H. These are the resins which are cation exchange resins, and the visuality is looking like this. It is highly porous in nature. It is having very good flowability. And to the para position, the sulfonated group is present, and this sulfonated group is nothing but SO3H group. And this sulfonated group undergo hydrolysis or ionization to get converted to SO3 minus and H plus, and this H plus will become responsible for the ion exchange process. So this is called as cation exchange resin. Very simple visual example in order to depict the cation exchange resin. Apart from this, SO3H resins, these are called as strongly acidic resins. Whatever the resin you prepare by using any organic substance, by immobilizing SO3H group, because SO3H sulfonic acid group is highly acidic, and these resins are called as strongly acidic resins. Even weakly acidic cation exchange resins can also be prepared. These weakly acidic cation exchange resins will be comprising the functional groups such as COOH, carboxylic acid functional groups. So these carboxylic acid functional groups will also undergo dissociation to get converted to carboxylate anion and hydrogen ion, where carboxylate anion COO minus is fixed to the polymeric surface and H plus ion is available freely for the exchange process. So this is also one of the examples in order to show weakly acidic carboxylic acid cation exchange resins. Weakly acidic carboxylic acid cation exchange resins. And similarly, you can look at this particular resin. This resin is also having the polymeric surface. To the para position of the benzene rings here, quaternary ammonium ion has been attached, CS2 NMe thrice plus OH minus. Here, plus charge is with respect to nitrogen, not with respect to Me thrice. So CS2 N plus Me thrice OH minus. Similarly, CS2 N plus Me thrice OH minus likewise. Here, OH minus is going to be the free ion. NMe3 is attached to CH2. Therefore, it can be called as, which is a functional group attached to the polymeric surface of the resin. So this is a very simple example for anion exchange resin in which the anions are going to be exchanged. the anions are going to be exchanged. If you take this resin, OH minus will be freely moving. Whatever the anion you are passing through the chromatographic column, the anions are going to be exchanged in place of OH minus ion, and the effluent will be containing OH minus ions equivalent to anions which have been replaced. So now you got the picture of cation exchange resin and anion exchange resin. So the exchange process is very simple to understand while using cation exchange resin and anion exchange resin, and the respective exchange process is called as cation exchange process and anion exchange process. Simply we can write any cation exchange resin which will be having a negatively charged sulfonate group or carboxylate group attached to the polymeric surface of the resin, and a freely moving mobile ion which is cationic in nature. So M plus ion is a cation which is carrying positive charge, and this is going to be used as a cation exchange resin. And this is going to be the stationary phase we will be using in cation exchange chromatography. Let us assume a solution containing the species AX, a solution containing the species AX, it is passed through the chromatographic column containing a cation exchange resin which is in the form of resin SO3 minus and M plus. This AX undergo rapid ionization to get converted to A plus and X minus, A plus and X minus. A plus is having greater affinity to get replaced by M plus ion. So all those cations, any cation it may be, you assume in place of A, any cation it may be, in place of X, any anion which is having the ability to get coordinated with A. So A is the cation which is obtained due to the ionization of the species AX. All those cations obtained by the ionization of the compound, those cations are going to be exchanged in place of M plus. You can see here. So A plus is replaced in place of M plus, and M is combined with the counter ion X which is moving through the chromatographic column, and this is going to be eluted. So this is cation exchange process. You assume a cation exchange resin in the form of hydrogen ion. In the form of hydrogen ion, SO3 minus is negatively charged group attached to the polymeric surface of the resin, and hydrogen ion is a free ion which is in motion, which is a mobile ion. If you pass a solution, dilute solution of sodium chloride through the chromatographic column containing a cation exchange resin in the hydrogen ion form, NaCl is having the ability to undergo ionization to get converted to Na plus ion and chloride ion. All those Na plus ions which are moving through the chromatographic column are exchanged in place of hydrogen ion to convert the resin into sodium form. So hydrogen ions were freely available, they were moving, they were in motion. So the affinity of sodium ion to get exchanged in place of hydrogen ion was more. Therefore, sodium ions have been exchanged in place of hydrogen ion, and hydrogen ion, whatever eluted, will combine with the counter ion chloride, and it will be eluted out from the chromatographic column. So this effluent can be subjected, for further investigation in order to quantify the solute. In order to quantify the solute, what is the amount of the solute which was exchanged? What is the amount of the ion which was exchanged in place of cation exchange resin cation? We can determine that by simply titrating this with a suitable titrant. So these two reactions will clearly explain the cation exchange process. Similarly, anion exchange resin you consider, the anion exchange resin will be having a anion which will be in motion, which will be freely moving. When you pass a solution, say AY is present in that solution, this will undergo ionization to get converted to A plus and Y minus. Y minus is going to be the anion, and it is having the more affinity to exchange X minus ion. So the resin which was trimethyl quaternary ammonium ion fixed cationic group, and X minus free ionic group which is anion responsible for exchange process, and Y minus is the anion obtained due to the ionization of AY. Y minus is exchanged in place of X minus to convert the resin into Y minus form. There is no any change. You can observe here, there is no any change for the fixed functional group positively charged species here and negatively charged species here. There is no any change going to be happen, but the negatively charged species is going to exchange the negative ion, the anion, which is freely available over the surface of the resin. You can consider a simple example, the resin which is present in hydroxide form. NaCl, if you pass through the resin which is in hydroxide form, chloride will replace hydroxide ion and hydroxide will combine with sodium to release sodium hydroxide. So these two processes are common processes we can expect always while performing ion exchange chromatographic separation, and these processes remain intact whichever the solute we are passing if it is ionic in nature. So all those ionic solutes can be better separated by means of this ion exchange chromatographic technique by using suitable ion exchange resins which are going to exhibit very good selectivity. Okay, so let us come to the definition of ion exchange chromatography further. It is a liquid chromatographic technique, we know this. It is a liquid chromatographic technique. Separation is based on the affinity of charged ions towards the polymeric resin of countercharge. As I explained, if you take a cation exchange resin, cation exchange is going to be taken place. If you take a anion exchange resin, anion exchange is going to be taken place. So the resin is having the affinity towards the charge spaces. The charge spaces present in the solution and the charge spaces present in the resin, they have affinity. Whichever the species having greater affinity, that will be exchanged rapidly, and whichever the species having lower affinity, that will be eluted rapidly. So this is the consequence for the serial elution of the ions from the chromatographic column. So depends upon the nature of the solutes we are going to separate and the nature of the resin. The ion exchange chromatographic technique will be classified into two types: cation exchange chromatography and anion exchange chromatography. The stationary phase in cation exchange chromatography will be a cation exchange resin, and in anion exchange chromatography, the stationary phase will be anion exchange resin. Mobile phase will be any liquid, say for example, sodium chloride or sodium nitrate or water most commonly, even potassium nitrate can also be used, sodium sulfate can also be used. Let us understand about them later. And the basis for separation in each and every chromatographic technique under ion exchange process, cation exchange equilibrium takes place in cation exchange chromatography, and anion exchange equilibrium takes place in anion exchange chromatography. So you can now better understand about the definition of ion exchange chromatography. So it is a chromatographic technique which is used for the separation of ionic solutes based on the relative affinities of the charged ions towards the polymeric resin of countercharge. So SO3 minus is the countercharge in the resin. So whatever the cations which are having the affinity towards SO3 minus, they are going to be exchanged. And similarly, N plus Me thrice is going to be the polymeric resin countercharge. And whatever the anions which are having the affinity towards that positively charged fixed spaces, all those ions are going to be exchanged. So the successful separation of ion exchange chromatographic method for solutes is dependent upon the property of the resin. Some properties must be exhibited by cation exchange resins and anion exchange resins. What are those properties? You will be using variety of the solvents including water. Whatever the resin you are going to choose must be insoluble in water and other organic solvents. Even up to 0.1% should not be expected. The solubility of the resin should not be even up to 0.1%. It should not dissolve. It must be insoluble in water and other organic solvents. If it dissolved, the ion exchange capacity will be declined. That resin is not going to be suitable. And it must contain active counter-free ions such as hydrogen ion or hydroxide ion or chloride ion or some other cations or some other anions. And these ions must be reversibly exchanged. The reversible exchange process must be expected. If you exchange hydrogen ions from sodium ions, we must be able to convert the resin which is present in the sodium form back to hydrogen ion form again. So The resin must contain active counter-free ions for the reversible exchange of ions in the solution if lightly charged without physical change. So physically, there should not be any change taken place. So it should contain active counter-free ion. Then the reversible exchange process must be expected. There must not be any physical changes occurred. And the resin must be highly cross-linked. These highly cross-linked resins will provide more number of exchangeable species. Therefore, if the resin is highly cross-linked, more the ion exchange capacity of that resin. And the swelling ability must be greater. If the resin swell properly, then the penetration of the sample solution or the diffusion of the solutes through the resin will become appropriate. The diffusion process is going to be taken place before the exchange process. So this diffusion will become comfortable whenever the swelling property of the resin is acceptable. Of course, these are polymeric in nature. They must have larger molecular mass. So you cannot prepare a resin with the lowest molecular mass. The resins must have larger molecular mass. If the resins are having larger molecular mass, and consequently all these four properties are expected. So these are the properties of resins.